Hi friends, we are in section 3.2 and we're looking at rational numbers, still in chapter 3. So let's see, we only have one vocabulary word today, and what I'd like you to do is actually write down the definition that I'm going to give you. So rational numbers are numbers that can be written as a ratio of two integers. So for any number that you can write as a fraction, basically, and a fraction, I mean a proper fraction, not like a decimal fraction combo or anything like that. If you have a situation where you can write 4 over 7, negative 5,000 over 9, whatever. If you can write a number as a ratio of two integers, you can best assure that you've got a rational number. Another way of looking at rational numbers is to say that you've got repeating or terminating decimals. So if it repeats, not just has a pattern that you can figure out, but if it literally has a chunk that repeats, then you know that you have a rational number. If it is a terminating decimal, meaning it goes on and on and on, but it does end at some time, then that is considered also a rational number. So what's not rational? The question that I would be asking right now is, well, what's irrational mean? So irrational, not necessarily a vocabulary word for this section, but I'm sure you're interested, so we'll talk about it. Irrational numbers are numbers that do not repeat and do not terminate, or numbers that you cannot write as a fraction. So for instance, pi. And I know we sometimes write that pi as 22 over 7, but that's just an approximation. Oftentimes when we have square roots that do not resolve, I can't take the square root of 2, nor can I take the square root of 3, and we can talk about the fourth root of things. I can't take the fourth root of 5. I can't find 5 integers, 4 of the same integers that multiply to give me 5, right? So when we cannot resolve something, it is irrational. Also, there's a number e that is irrational. There is also a whole section of numbers that are imaginary. So imaginary numbers refer to, I'm going to put a block right here. Imaginary numbers refer to numbers with I in it, I being the square root of -1. So the vocabulary word that you need to know for this section is rational numbers. Let's take a look at some examples. So here is example 1, and we're looking at mixed numbers and writing integers as fractions. So we're going to write mixed numbers and integers as fractions, which I know you guys know how to do. When we talk about writing as a fraction, we're going to write it as an improper fraction, so again as a ratio of one number over another, or one integer over another. And I'm hopeful that you guys remember that to change a mixed number into a fraction, you multiply the whole number times the denominator and add the numerator to create a new numerator, and then your denominator stays the same. So this would give us 37 over 6. And that's how you'd write that as a rational number or as a fraction. So here we have -23 over 1, because anytime we have a whole number, we put it over 1, we create a fraction. And that's all for example 1. Let's take a look at example 2. Here in example 2, we're going to write a terminating decimal as a fraction. So this is something that you should have done. I am going to talk about it in the way that I do it. If you have another way, I'm sure it's just as logical and just as good, but I'm going to talk about it this way because I think it's going to work every time, everywhere, okay? And so what I'm doing is I'm taking 0.64 or 0.64, and I'm going to put it over the number 1. Remember last example we had, we put a whole number over the number 1, and what we found is that it didn't change the value. Similarly here, putting a whole number over, or any number over the number 1 doesn't change the value. However, I have not answered the question. We're going to write it in a fraction in its simplest form, and this is not an acceptable fraction. Do you know why? Because I've got that decimal in there. To get rid of the decimal, I need to either move the decimal place over a few times, in this case 2 places, and what that means ultimately is that I'm multiplying by 100. So what I do to the top, I've got to do to the bottom. When I do that, I get 64 over 100. Some of you would have looked at this value and gotten 64 over 100 anyway, because you recognize that to read this number is 64 hundredths. That's perfectly fine as well. So now, to get it in its simplest form, what I'm going to do is reduce as best as I can. I'm going to look for a number that divides evenly into the numerator and the denominator. 2 is an obvious one. If you look more closely, you can see that 4 also goes into the numerator and denominator as well. If you chose 2, then you'll just keep working at it until you get it so that they have no more common factors. 64 divided by 4 is 16, and 100 divided by 4 is 25. These guys no longer have common factors, and so I know that I'm done. All right, so let's go ahead and see if we can do another example. This next example actually is more challenging, and I want you to really pay attention. Ask me questions in class about this one. I'm expecting questions in class, so don't feel some type of way. That doesn't mean you can't understand it here. It just means you're going to need some more practice with it in order to really have a good understanding of it. So let's take a look at example 3. In example 3, we are starting off with a repeating decimal, and we know that this means that 6 is going on and on and on forever and ever after the decimal point, right? And so what we're going to do is we're going to write it as a fraction. There's a trick to this, and it requires algebra, which is weird because we're in pre-algebra, but let's get started anyway. We'll first start by saying n is equal to 0.666 repeating, okay? The next thing we'll do is we will consider what can we multiply this n, or this 0.666 repeating, by in order that I get another number that has 6's repeating after it as well, after the decimal as well. And the simple answer is that I'm going to do 10 times n. When I multiply 10 times n, or let's put it over here, 10 times n, I'm going to do what I do to one side of an equal sign, I have to do to the other to maintain equality. When I multiply this by 10, what I end up with is 6.666 repeating, all right? Hold on to that concept, because now this is where things are going to be a little bit crazy, but that's okay, you guys are tough. What I'm going to do with these two numbers is get rid of the repeating part, because that's kind of hard to deal with sometimes. So if I take 6.66666 and take 0.66666, if I subtract them, I get rid of the repeating part. So 6.66666 minus 0.66 repeating, right, is going to end up giving me 6. But what I do to one side, I've got to do to the other. So I end up with 10n, which is 6.66666, minus n, which is 0.666, which is the same thing, and 10n minus n is just 9n. Not 10, but 9n, because if I got 10 n's and I take one n away, I'm left with 9 n's. All right, so now where do we go from here? Well, if 9 times a number is equal to 6, to get this number, I'm going to have to divide by 9. If 9 times something is equal to 6, then if I divide both sides by 9, remember what I do to one side, I got to do to the other, I'm left with n. So n is equal to 6 over 9. You know how we do. We like to reduce fractions. 3 goes into both of these, so I'm left with 2/3. And if you remember, 2/3 is certainly equal to 0.666 repeating. So n is what we started with as a decimal, and n is what we ended with as a fraction. All right? I hope that makes sense. We're going to go on to a couple more examples. Though example 4 is our last example, we have a few examples in here. So not a couple more, a few more. So let's go ahead and take a look. We're going to identify all sets to which each of these numbers belong. So let's go back and think about the sets of numbers that we know about. So we have several groups of numbers that we talk about in math. One is the natural numbers. Natural numbers are numbers that you guys are really familiar with because you've seen them before. They're counting numbers, right? Sometimes I call them kindergarten numbers. So 1, 2, 3, 4, 5, 6, 7, 8. Then we have another layer, which is whole numbers. Whole numbers include the natural numbers, right? But whole numbers also include the number 0. So whole numbers basically add to the list of natural numbers 0. So whole numbers. I'm going to use that symbol there. Sorry for this being sloppy. That word is whole, W-H-O-L-E. All right. So then the next set of numbers that we can branch out and think about would be integers. Integers are negative and positive whole numbers. So sometimes I call them number line numbers. They're numbers that go -5, -4, -3, -2, -1, 0, 1, 2, 3, 4. So you see they contain all of the whole numbers, they contain all of the natural numbers, and they also contain the negatives of the whole numbers. Make sense? All right, so now stepping outside of that we have rational numbers. And for the most part, your years here, we're going to talk about rational numbers. So rational numbers, you remember we defined as negative and positive, not negative and positive. They are negative and positive, but any number that we can write as a fraction or as a terminating or as a repeating decimal. That's a lot of numbers. There are further categories that we're going to leave alone, but you know, so if these are the rationals, over here we have the irrationals. And we talked a little bit about what irrationals are. So we've got pi and square root of 2 and all kinds of stuff that don't resolve nicely. Let's go ahead and now we're going to classify each of these numbers into a set. So when I look at this number, I recognize that it's not a natural number. It's not a whole number. It's not an integer either, but it is rational. I can write this as a ratio of 2 integers. So this is a part of the rationals. This number here looks really interesting. 1.313313331, I would assume that it would go 33331. And since I see the pattern and I get it, it seems like it's repeating, but it's not. It's a pattern, but I don't have a chunk that just repeats. So because of that, I'm not going to classify it as rational. Clearly, it's not natural or whole or integers because those deal with whole numbers that are negative or positive. What I see here is that it's not in the category of rational either because the repeating part isn't, it's more of a pattern and not repeating. So this has to be irrational. And over here, the number 45. Number 45 is natural. If I count, for starting with 1, going up by whole numbers, I'm definitely going to get to 45. The fact that it's natural and it's in the center of these concentric kind of circular things, then it's everything else. So it's natural, it's whole, it's an integer, and it's also rational. All right. So guys, as always, I really look forward to hearing your questions, particularly about example 3. That was a little crazy, right? But if you let me sit down and talk to you about it, I think it'll make sense. If you already got it, kudos to you. Make sure you try those problems and still talk to me about it anyway. I look forward to seeing you guys soon. Please have a good day and do good work. Take care. Bye-bye.